Hi, I'm Fernando Pereira from UFMG, and today we conclude our overview of JIT compilation. We shall talk about a particular kind of JIT compiler called a trace compiler. A trace-based JIT compiler translates to binary only paths within the control flow graph, not the entire function. So it profiles the function CFG and associates branches with counters. Once a certain threshold is met, it translates the profiled path into binary. One of the most well-known trace JITs was TraceMonkey, used in the Mozilla Firefox browser. This figure shows the main components of this engine. It was built into SpiderMonkey, the JavaScript interpreter used in Firefox. That trace JIT would reuse lots of other components implemented elsewhere, but don't worry, its implementation is not really important. Let's focus on what it does. TraceMonkey is part of SpiderMonkey, which is a JavaScript interpreter. Given a program like this one on the left, SpiderMonkey produces and interprets a representation like this one on the right. Once a loop is found, SpiderMonkey calls TraceMonkey to convert this loop into binary. Not the entire loop, but a path within the loop actually. TraceMonkey works in a program representation called LIR, which means low-level intermediate representation. One thing that's interesting is that in the process of converting code to LIR, TraceMonkey does some type specialization. Whenever possible, it converts numbers to integers, otherwise they would be floating point numbers like every number in JavaScript. In this process, TraceMonkey inserts lots of overflow checks in the program. You can see two of these overflow checks in this code due to an add instruction and an inc instruction. These guards, the overflow checks, they are necessary because floating point numbers can assume higher or lower values than integers. Then, to preserve the semantics of the program, it's necessary to guard them, the operations that manipulate numbers against overflows. So, to summarize, it's better to work with integers whenever possible, but we need to provide for the situation in which those numbers cannot really be represented as integers. And the overflow checks end up being translated into binary. They can slow down the program, of course, because there will be more branches in the code, so it would be good to remove these checks. But how to do it? We can use range analysis, and because we are working on traces, which are code snippets without branches, we can design a much simpler and faster algorithm than the one we had seen before. And because we can check runtime values, this algorithm will be much more precise. I will illustrate it with this example program on the left. We don't actually know the number of iterations of the loop by just looking to the program. However, we are generating code at execution time, so we can check the value of n in the interpreter's stack. That will let range analysis be more precise. So how does the algorithm work? We will create a constraint graph and propagate ranges along this graph. Then we will use the solution of these constraints to eliminate some overflow checks. Our graph will have different kinds of nodes. There will be nodes for names of variables, nodes for arithmetic operations, nodes for relational operations, and one type of node that we will use to denote assignment. Let's see how we can generate this graph for this program on the left. This is the trace that we had seen originally in this class in the example. Given the way a trace compiler works, we usually start generating the graph from the end of the trace because that's when the trace compiler really starts translating the instructions marked in the trace to binary. We will generate nodes for the less than comparison. We need nodes for the two variables that are used in the comparison. The first is n, At the moment the trace is produced, the value of n was 10. So 10, 10 is the interval of n. Then there is I. When the trace was compiled, I had the value 1 in I. So its interval will be 1, 1. The less than comparison yields this pattern. We rename the variables after every comparison. In practice, we are building some sort of extended static single assignment form. Do you remember this representation from the range analysis class? It renames variables after conditionals. Now we move to the beginning of the trace. There is a sum there. We need to read the operands. The first is called, sum. We create a node for it. Its range is 1, 1, because that's the value of sum in the stack of the interpreter when the trace is compiled. Then we create the add node, linking its input operands. We produce a new name for sum, because that's like a redefinition in an SSA form program. We also create a node for the inc instruction. This instruction also defines a new name, I2 in this case. Notice that every arithmetic operation creates a new name, just like in SSA form, but this is like a dynamic view of SSA form because we are creating it while the program runs. Some variables have never been updated in the trace. N is an example, so we know that n is constant. Other variables like sum have been updated. Then we know that they cannot be constants. Notice that the comparisons let us place bounds on variables. We can use the constants to limit the ranges of the non-constant variables in the conditionals. So to propagate ranges, we widen the ranges of all the variables that are not constant. Then we use the conditionals to narrow them back into bounded ranges whenever that's possible. So we get that I1 can be at most 9 because it's less than n, which is 10. We keep propagating ranges. An addition of minus plus infinite with anything yields back minus plus infinite, of course. And if we increment minus infinite 9, then we get minus infinite 10, right here, the range of I2. Once we know the ranges of the variables, we can check which operations still require overflow tests. We need an overflow guard for add because it returns a variable that can be plus minus infinite, right here. However, we do not need a check for the inc operation because it returns at most 10, so there's no way this can overflow. Then we can eliminate one of the overflow checks, the one used to guard the inc operation. The other will still be there. We have to leave it in the program because we couldn't really get enough information to remove it. And with this last optimization, we close our class on JIT Compilers. This algorithm that eliminates overflow checks was taken from this paper presented in CC 2011, Dynamic Elimination of Overflow Tests in a Trace Compiler. The notion of value specialization in JIT compilers that we saw in the previous class was explored in the paper Just-in-Time Value Specialization. Thank you.